Hello students, let us now discuss in this session the another alkaloid. The last alkaloid that is remaining is nicotine. Nicotine. Now, nicotine is a colorless liquid with tobacco smell. It is the most important tobacco alkaloid occurring in Nicotina tabacum and other Nicotina tiana species. It usually occurs in the form of its salt. Okay. Now, isolation. Tobacco leaves or bark is powdered and extracted with dilute acids. Water-soluble salts of alkaloids are thus removed in the solution, leaving behind insoluble plant material. So the main thing that we need to concentrate is based on its structure of nicotine, of the constitution of the nicotine, and then its synthesis. So the first thing that is done is molecular formula. From the analytical data and the molecular mass determination, it was found that the molecular formula of nicotine is C10H14N2. Okay, so this was the structure of, this is the molecular formula of nicotine. Second one is nicotine when treated with methyl iodide. Nicotine when treated with methyl iodide, it forms dimethyliodide and two monomethioides. It does not react with acetyl chloride. Okay, it does not react with acetyl chloride. Acetyl chloride is CH3C double bond OCl. It does not react with acetyl chloride or benzyl chloride. It clearly suggests that both the nitrogen atom in nicotine are tertiary. Both the nitrogen atom are tertiary in nature because it does not react with acetyl chloride or the benzyl chloride. Hence, both the nitrogen atom are tertiary in nature. One of the nitrogen atom present as NCH3 group is determined by Herzig-Meyer method. See, this nicotine contains two nitrogen atoms. Both the nitrogen atom are tertiary in nature because this does not react with acetyl chloride. Because if the nitrogen atoms are primary or secondary, then they react with acetyl chloride. Generally, N-acetylation takes place. For example, if there is a compound like this, RNH2 or secondary RNH. So when treated with this, when treated with acetyl chloride, what happens is generally N-acetylation takes place. So you get this compound RNR N C double bond O, this is N C double bond O CH3 is what you get. When this is treated, this is what you are going to get. RNR C double bond O CH3. You are going to get N acetylated product is what you are going to get. So if this is primary or secondary, but this nicotine does not react with acetyl chloride. That means the nitrogen atom is tertiary in nature. If it is tertiary, it does not react generally. Okay, this was one thing. Next, nicotine when oxidized with chromic acid, nicotine that is C10H14N2, when subjected to oxidation, it forms nicotinic acid. It forms nicotinic acid. Okay, nicotinic acid is pyridine beta carboxylic acid. So it shows that nicotine is a pyridine derivative. So we don't know the structure of nicotine, but on oxidation it gives you this molecule. That means it gives you pyridine carboxylic acid is what it gives. It gives you pyridine beta carboxylic acid. We call this as nicotinic acid, right? So it gives you nicotinic acid. Nicotinic acid is a pyridine beta carboxylic acid. That means this nicotine should contain a pyridine molecule. That is, it is a pyridine derivative with a side chain in beta position, with a side chain in a alpha as well as a side chain in a beta position. Okay, so from this it was confirmed that uh, nicotine contains a pyridine nucleus. Now, next one is the nature of the side chain. Next one is the nature of the side chain. Right. Now, nicotine forms an addition compound with ZnCl2, which on distillation with lime gives you pyrrole and pyrrolidine and methylamine. See nicotine. Nicotine I mean C10H14N2. When treated with ZnCl2, it forms an addition compound. When it is distilled with lime, you get pyridine, pyrrole, and methylamine. Pyridine, pyrrole, and methylamine. Okay, it gives pyridine, pyrrole, and methylamine is what. Therefore, the side chain, that is C5H10N in a pyrrole derivative. Okay, so therefore the side chain should be a pyrrole derivative. That means a pyrrolidine ring is present. See, we know that nicotine contains a pyridine nucleus. We know that nicotine contains a pyridine nucleus with a side chain at a beta position. So we know that it contains a pyridine nucleus. How did you get that it contains a pyridine nucleus? Based on that oxidation. Nicotine on subject, when subjected to oxidation, gives you nicotinic acid. It gives you nicotinic acid. So nicotinic acid is a pyridine molecule. I mean pyridine carboxylic acid. So nicotine also should contain a pyridine nucleus. The other question is, in beta position there is a substituent. Okay, that substituent is a pyrrole derivative only, because on distillation you are getting a pyridine as well as a pyrrole. That means this pyrrole and pyridine should be linked together. Okay, it should be a pyrrole derivative. That is, it will be generally a pyrrolidine ring will be present. Later on we'll see that. Okay, now when nicotine is heated with concentrated HI at 200 to 300 degrees Celsius, methyl iodide is formed. Thus methyl group is attached to nitrogen atom. Okay, it appears that the side chain should be N-methyl pyrrolidine. The side chain should be N-methyl pyrrolidine. See, let us sum up everything. Nicotine does not react with acetyl chloride. Hence, the nitrogen is tertiary. Nicotine on oxidation will gives you nicotinic acid, that is a pyridine carboxylic acid. Right? It gives you a pyridine carboxylic acid. So this confirms that nicotine contains a pyridine ring, and to beta position there is a substituent. So we should know which substituent is present. So pyridine, when treated with ZnCl2, forms an addition compound. When heated, it gives you pyridine as well as a pyrrole derivative. Pyrrole. So this confirms that pyridine nucleus is attached to a pyrrole derivative. The pyrrole derivative is pyrrolidine only, because if you look at the formula, if you remove it, what the part, the side chain should be C5H10N. The side chain should be C5H10N only. So C5H10N means it should be pyrrolidine ring only. And when nicotine is heated with HI, methyl iodide is formed. So thus methyl group is attached to the nitrogen atom. Okay, the point of attachment of the pyrrolidine ring to the pyridine ring. This is pyrrolidine ring. This is the pyrrolidine ring. So the point of attachment of pyrrolidine ring to the pyridine ring is determined by graded oxidation method. Okay. Now, nicotine reacts with methyl iodide to form nicotine isomethionide, which on oxidation with K4 efficiency gives nicotine. This on further oxidation with CrO3 produces hygrenic acid. In this reaction, pyridine ring is oxidized. This clearly shows that C2 of N-methyl pyrrolidine ring is attached to C3 of pyridine ring. Let us explain this. Okay, now what is that is if I take nicotine C10 H14 N2, if it is treated with HI and then with methyl iodide, okay, okay, it forms nicotine isomethionide C10 H14 N2 CH3I. This on oxidation with K4 efficiencies, potassium ferrocyanide, K4 efficiencies will give you nicotone C10 H13 N2O CH3. Okay, this on oxidation with CrO3 will give you this compound. Hygrenic acid. Now, in this process, the pyridine nucleus is see. We know that nicotine contains a pyridine nucleus and pyridine is attached to a pyrrolidine nucleus. Both these are attached. These are attached. We want to know where they are attached now. This reaction, in this reaction, pyridine gets oxidized. This reaction, pyridine gets oxidized. So if when pyridine gets oxidized, at this position, what is happening is a COH group is present. That means at this position only the pyridine nucleus should be present. So from this it is confirmed that C2 of N-methyl pyrrolidine, that is C2, second carbon, that first C2 of N-methyl pyrrolidine is attached to C3 of pyridine ring, because when pyridine was oxidized, when nicotine was oxidized, we obtained this. In this reaction, pyrrolidine nucleus was oxidized and we got a substitute at this position, third position. Now in this reaction, pyridine is oxidized and we are getting a substitute at this position. That means both this should be connected like this. That is, third carbon of pyridine should be connected to second carbon of N-methyl pyrrolidine. Okay, hence the structure of nicotine was given like this. So at point of attachment will be third carbon of this and second of this. This was the structure of nicotine. Okay, now the further support, we can go for the formation of nicotinic acid and the hygrenic acid. Okay, now let us go for it. Now, okay, let us discuss everything in one shot only. This is nicotine. This is nicotine. Right? Nicotine on oxidation gives you nicotinic acid. Right? We have discussed this. Right? In this process, what is happening? This nucleus is getting oxidized and we are getting a substitute at this position. That means the point of attachment is this. This when treated with HI. and methyl iodide. What you get? You get methiodide. This is what we had discussed. We get methiodide. I will just draw the structure of that. You get this methiodide. When this is treated with K4FeCl6, when this is treated with K4FeCl6, you get nicotol. This is what you get. This one oxidation gives this acid. Look at this now. Nicotine or oxidation, this part get oxidized and you get a substitute at this position. By this method, this part gets oxidized and you get a substitute at this position. That means this position and this positions are both linked. So that is why the structure of nicotine is like this. Okay. So further, the structure of nicotine was confirmed by its synthesis. Okay. Its synthesis. Let us go for the synthesis.